Hello. So far, we've discussed two important logical properties. One of them is logical equivalence, which applies to pairs of sentences. The other one is logical truth, together with its partners, logical falsity and contingency, and which pairs on individual sentences. Now we're going to focus on arguments, since we're going to discuss validity. As you remember, in a valid argument, whenever the premises are true, the conclusion is true as well. Equivalently, we can say that a valid argument makes it impossible for its premises to be true and its conclusion false at the same time. If such a thing were possible, we would say that the argument is invalid. We have already seen that we can define and test equivalence and logical truth on truth tables, and we can do the same with the validity-invalidity dimension. Suppose you have an argument with a conclusion and two premises. I'm choosing two for purposes of illustration only. The number of premises is unimportant. Then we make a column for each of the premises and one for the conclusion. Then, following our definition of validity, if our argument is valid, then there is no row in which all the premises are true and the conclusion is false. Notice that both conditions have to be present in a single case. True premises, false conclusion. All other combinations of values are admitted. The only one that is forbidden is true premises and false conclusion. This is so important that I'm going to elevate it into a definition. An argument is valid just in case there is no row in which its premises get T's and its conclusion gets an F. Otherwise, it is invalid. So, if we find a single row in which all the premises get T's and the conclusion gets an F, we declare the argument invalid. This row, by the way, is called a counterexample to the validity of the argument. More specifically, a counterexample to an argument is an assignment of truth values to atomic sentences, that is to say, a truth table row, where all the argument's premises are true, but the conclusion is false. Let's give an example. Take this argument. Either Amy will go to Paris or Bill will go to Omaha. Amy will not go to Paris. Therefore, Bill will go to Omaha. It seems good, at least intuitively. But let's use a truth table to check whether it's indeed valid. Symbolizing, we get this. Notice that we use three dots in place of the word therefore. The three dots then always occur before the conclusion of an argument. Here I've completed all the columns. There is one column for premise 1, another column for premise 2, and yet another one for the conclusion, which is B. And so it happens to be the same as our second column from left to right. I'm just repeating it here for clarity's sake. You don't have to do that. Now I've added a column where I will write whether the row at issue constitutes or not a counterexample to the validity of this argument. Okay, so let's search for counterexamples. Remember that we are trying to find a row that has these two elements, T's under both premise 1 and premise 2, and F under the conclusion. So the first phase of our search is to look for a row where both premises are true. This doesn't happen in our first two rows, since premise 2 is false in both of them, so neither of them is a counterexample. Row 3 is more promising, since both premises are true there. However, the conclusion is true as well. In consequence, this is not a counterexample either. Finally, row 4 is not even a candidate for being a counterexample. So we've searched all the rows of this truth table, and in so doing, we've gone through all the possible cases, and we've found that none of the possible cases is a counterexample. Hence, this argument has no counterexamples and is therefore valid. Now let's do another example. Determine whether this argument is valid. To do so, we make a truth table and assign a column to each of the premises. Premise 3 is A, which is our first column, and the conclusion is C, which already occurs as our third column. I already filled the columns for not A and not B, and I'll let you fill in the rest of the table. So if you want, pause the video while you work through the truth table. Are you done? Okay, let's zero in on the rows in which both premises are true. The only one that fits the bill is row 1, so we can ignore the rest. And what happens to our conclusion there? The conclusion is true, so it's not a counterexample, so the argument is valid. Okay, so far we've talked about validity. Implicitly, however, we've also talked about invalidity, which is the other side of the coin. As you know, an argument is invalid if it's not valid, and vice versa. So an argument is invalid if and only if it is possible for its premises to be true and its conclusion false. In terms of truth tables, an argument is invalid if and only if there is at least one row in which the premises are true and the conclusion false. That is to say, the argument is invalid if it has at least one counterexample. So when you look at it, what we did in our previous two examples is to test for invalidity. And since we failed to show invalidity, we declared the argument valid. But now look at the following argument. Either Amy will go to Paris or Bill will go to Omaha. Amy will go to Paris, therefore Bill will not go to Omaha. Is this argument valid? Well, first, let's symbolize. And this is what we get. A or B, A, therefore not B. Now let's check with the truth table. We can see that the first row is a counterexample, since both premises are true, while the conclusion, which is not B, is false. So this argument is invalid. Now let's do another example. Take this argument and show that it is invalid. But first, start by doing the truth table. So again, you can pause the video while you do it. Okay, let's look at the complete truth table. The first step is to look for columns in which both premises are true. Only rows 3 and 4 are good in this respect. And if we look at row 4, we can see that it does constitute a counterexample, since the conclusion comes out false there. So row 4 shows that it's possible for this argument's premises to be true while its conclusion is false, and in consequence that it is invalid. Now let me mention an asymmetry, which you may already be aware of. Notice that for showing invalidity, we must take into consideration all the rows in a truth table. For invalidity, it is different, since in principle, one row is enough for establishing it. Okay, let's point out some interesting relations between the logical properties we've studied so far. I'm sure you noticed that there were some remarkable parallels between conditional sentences and arguments. Suppose you have an argument that says the following. Neither Al nor Beth is a singer. Therefore, Beth is not a singer. Now consider the conditional. If neither Al nor Beth is a singer, then Beth is not a singer. Now, I'm doing different things by uttering 1 and 2 on the one hand and 3 on the other. If I utter 2, which is the conclusion of the argument, I am asserting that Beth is not a singer. Whereas if I utter 3, the consequent of the conditional, in the context, again, of saying the conditional, I'm doing no such thing. What I'm doing is that I'm conveying that there is a relation between the truth of the sentence, Beth is a singer, and the truth of the antecedent sentence. I'm not asserting that Beth is a singer. Nevertheless, we can see that there are parallels in terms of structure, and in fact, you can always turn an argument into a conditional sentence, and vice versa. So take a look at 4, a conditional sentence. So it has an antecedent, which is not A or B, and a consequent, which is not B. To turn it into the corresponding conditional, we simply make the antecedent into a premise and the consequence into a conclusion, and we get this. Okay, so now look at this argument. Here we have more than one premise, so to turn it into a conditional, we start by conjoining the two premises, using the ampersand, of course. And then we make that conjunction into the antecedent of our conditional, with the conclusion as our consequent, and we get 7. Okay, now we know that there is a one-to-one correspondence between arguments and conditionals. Now we'll turn our attention on a property of conditional sentences, namely logical truth, and we'll see how it relates to the validity of an argument. Let's suppose that we have a conditional sentence that is one of the general form X horseshoe Y. Assume also that this sentence is a logical truth. Now remember that not all logical truths are tautologies, since tautologies are a special kind of logical truth that is studied in sentential logic. Tautologies are sentences that are logically true simply in virtue of the meaning of the truth-functional connectives. However, we also stipulated that, provided we are discussing sentential logic, we can use the terms tautology and logical truth interchangeably. Okay, so let's go back to our discussion. X horseshoe Y could be any conditional tautology. It could be if A and B then B, or it could be if A, then A or A, etc. Now, what would the truth table look like? Well, given that it is a tautology, it would come out true in every row. And how do you guarantee that a conditional sentence is going to be true in every single row? Well, we know that a conditional is only false in one particular case, namely in a case in which the antecedent is true and the consequent is false. So given that X is the antecedent and Y the consequent, then we can conclude that if X horseshoe Y is a tautology, then its truth table contains no row in which X is true and Y is false. Also, remember, keep in mind that X horseshoe Y is a tautology, and therefore there is no assignment in which X is true, but Y is false. So with that understanding, let's take X and Y and make them into the premise and the conclusion of an argument, respectively. So we have the argument X, therefore Y. This may not look valid, but remember that both X and Y could be substituted with compound sentences, as we mentioned before when we talked about the conditional. Let's check the truth table. Let's make one column for X, which is the premise, and one for Y, which is the conclusion. We know from our previous discussion that there is no row in which X is true and Y is false. This means that there is no row in which the argument's premise is true and its conclusion false. Hence, the argument has no counterexamples, so it is valid. This illustrates that to every logically true conditional sentence, there corresponds a valid argument, formed by taking the conditional's antecedent as premise and its consequent as conclusion. In other words, if X horseshoe Y is a logically true sentence, a tautology, then X therefore Y is a valid argument. It works the other way around too. Suppose X therefore Y is a valid argument. This means that there is no assignment in which X, the premise, is true and Y, the conclusion, is false. But if so, then the conditional form by taking X to be the antecedent and Y the consequent will also be true in every row, because there is no row in which the antecedent is true and the consequent false. Hence, that conditional will be a tautology. So, if X therefore Y is the valid argument, then X horseshoe Y is a logically true sentence. In sum, X therefore Y is a valid argument if and only if X horseshoe Y is a logically true sentence. Let's give an illustration. Sentence 8 here is a conditional. The truth table reveals that it is a tautology. It is always true because there is no row in which not A or B is true, while not B is false. What happens if we turn 8 into an argument? We get 9, the argument that has not A or B as premise and not B as conclusion. Its truth table shows that the argument is valid, since, as we already knew, there is no row in which its premise is true, while its conclusion is false, since not A or B is its premise and not B is its conclusion. So, there is a one-to-one correspondence between logically true conditionals and valid arguments. The fact is interesting in itself, but it also will come out handy later on when we discuss rules for doing derivations. There is a corresponding fact linking biconditional sentences and the property of logical equivalence. If two sentences X and Y are logically equivalent, then the sentence X triple bar Y is logically true, and vice versa. That is, if X and Y are logically equivalent, then the sentence formed by taking X and Y and joining them by the triple bar is a tautology. We can see why this is the case. If X and Y are logically equivalent, then they have the same truth value in every row of their truth tables. Whenever one is true, the other one is true, and when one is false, the other one is false. We also know from the evaluation rule for the biconditional that if in a given row both components X and Y have the same truth value, X triple bar Y comes out true. If they differ, then X triple bar Y is false. Now, in the case we are considering, the fact that X and Y are logically equivalent guarantees that X triple bar Y will be true at every row. Therefore, the biconditional is a tautology. Okay, an example. As we know, these two sentences are equivalent. and their truth table illustrates this. In consequence, the sentence formed by joining those two sentences by a triple bar is true at every row. And so it's a tautology. Okay, this is all for this video. Goodbye.